The Center for Ultrafast Optical Science is a center in the College of Engineering in which we study very, very short pulses of light created by lasers. High field science is basically the regime where the intensity of the light is so strong that the electric field in the laser spot becomes really extraordinary.
High field science is a really exciting research area to work in. We're able to access such high energy densities that can only be created on this Earth using these very high intensity laser pulses, creating plasma conditions that would otherwise be found in enormous astronomical objects. We recreate the physics around these objects on a much tinier scale using these very high intensity laser pulses.
Although this field of science is relatively new, there are several applications for science and technology. Those are connected to two features of ultrafast lasers. First, the pulse brevity and also the high intensity that can be generated with this pulse.
The radiation created by high-power lasers can be potentially used for medical imaging using the X-rays, for homeland security applications, for detecting explosives and nuclear materials. They can also be used for medical applications, for proton therapy, generating efficient and compact sources of energetic protons for cancer treatment. At the Center for Ultrafast Optical Science, we have the Hercules laser. The Hercules laser was constructed about 10 years ago and was funded by the National Science Foundation. And we presently have the world record for peak intensity.
Hercules actually is an acronym that means High Energy Repetitive CUOS laser system. And it took quite a few years to develop. Hercules laser has a peak output power 300 terawatt. It's reasonable to compare it to the output power of the United States electrical power grid, which is about terawatts. So we have power which is 300 times higher.
We use Hercules then as a very compact source of very energetic electrons. And those electrons can be up to a GeV in energy and be accelerated on over the distances of only a few centimeters. So it has the largest laser wake field acceleration, and it has the largest acceleration gradient in present-day technology.
We create very small millimeter scale plasmas. The plasma is already broken down, so it can support huge electric fields, and therefore the particles can be accelerated over very short distances. So we can condense the acceleration lengths from hundreds, maybe thousands of meters into just a few millimeters.
The Hercules laser promises to make accelerators much more compact and much more efficient and much cheaper.
Ultra-high intensity lasers provide a bridge between optics and nuclear physics and physics of elementary particles. That potentially means to build an accelerator that is not possible to build by conventional technology.
We're on the cusp of entering a quantum electrodynamic plasma regime where not only will we have plasma physics, but we'll have prolific pair production, very bright, dense bursts of very high energy photons, gamma rays, and this will enable new physics to be studied.
Well, our goals in the future are to drive this technology forward, to always be at the cutting edge of laser intensity and in the physics frontier of these very relativistic plasmas. We want to study the science at this frontier, but we also want to be leaders in the technology and applications. We want to show some practical realization of these very unique lasers and how they can be made to be useful for society.